Welcome to Math Essential Vector Calculus. Today we'll discuss about the del operator, one of the most important parameters when discussing vector differentiation. The purpose of this video is first to define the Nabla operator and understand its meaning, show how it transforms between different coordinate systems based on the scale factors, and finally prepare for the gradient, divergence, and curl in later episodes. Let's have a fast recap in the coordinate systems on the infinitesimal length of the differential position vector. So delta L is equal to some scaling factor multiplied by the differential and then multiplied by the unit vector in each of the coordinates. And the scaling factor we have calculated together before. If you have a length, there is no scaling factor, it is just one. So this is also a length, this is also a length. All of these are lengths, so you'll always find that the scaling factor is equal to 1. But once you have an angle, either theta or phi, then you will have some scaling factor. So the scaling factor in case of phi, it will be rho, and actually r sine theta is just also rho, and the scaling factor in case of theta is r. The differential operator in case of the Cartesian coordinate will be dx dy dz, cylindrical coordinate d rho d phi dz, and of course in the spherical coordinate system we'll have dr d theta and d phi, and finally the unit vectors we have ijk in case of Cartesian, rho phi z in, or k in case of cylindrical, and r theta phi in case of the spherical coordinate system. Now we move to the main topic today, which is del and nabla, starting with the definition. So del or nabla is a differential operator in vector calculus, and based on the operation and also the field type, either scalar or vector field, we will have three different tools. So the first tool will happen if we have a scalar field and we apply nabla to it, and this one actually is just what's called the gradient. Second one, when we have a dot product with a vector field, we will have in this case what's called divergence. Last one is when we have a cross product of nabla with a vector field, and this time we'll have another one which is called the curl. Of course, we will have more details about each of these in independent videos. Now we move to the general expression of nabla or del. Del, this is its symbol which we'll use, is equal to 1 over h1 partial by partial u1 in the direction of a1 plus 1 over h2 multiplied by partial u2 in the direction of a2, finally plus 1 over h3 multiplied by partial u3 in the direction of a3, and of course h1, h2, hc are just the scaling factor, and they describe how the distance change with the coordinate system. This section will show nabla in the 3D coordinate system which we studied, starting from the Cartesian, and this is the simplest one. We just multiply the partial by partial x, partial by partial y, partial by partial z by I, j, k, and of course there's a plus sign in between. In case of cylindrical coordinate system, only the term which is multiplied by phi will appear 1 over rho. And finally, in case of spherical coordinate, since we have two angles, so the phi term and the theta term will be multiplied by 1 over r and 1 over r sine theta respectively. So let's wrap up this video. We have started about the nabla or del, which is a vector differential operator defined by the scaling factor, and based on the coordinate system, the value of the scaling factor will change. Basically, when we have an angle, we will have a value for the scaling factor, otherwise it will be just 1. And in the following slide we'll start one of these differential operations, which is the gradient, which is used to measure change in scalar fields.